Imagine a pianist recording in a music studio. He invites you for a game. The game is to guess the musical notes that he plays without looking at the piano. But you can guess the musical note just on hearing. What will you do to win the game? It is simple. Just record his notes in auto editing software. This converts the notes to a waveform, then apply Fourier transform to figure out. Because Fourier transforms are performed using complex numbers which help to identify which frequencies are most prevalent within the recording. In this video, we will discuss some concepts related to complex numbers. We will indulge in discussing how to find the modulus and conjugate of a complex number. Modulus and conjugate of a complex number. The modulus of a complex number gives the distance of the complex number from the origin in the Argand plane, while the conjugate of a complex number gives the reflection of the complex number about the real axis in the Argand plane. Before further going to its detail, let's discuss its representation of a modulus of a complex number. Let z is equal to a plus ib be the complex number. Then modulus of the complex number z is denoted by modulus of z is equal to a non-negative real number, that is square root of a square plus b square. Next we'll see representation of a conjugate of a complex number. For the complex number z is equal to a plus ib, conjugate of a complex number z is denoted by z bar and it is written as z bar is equal to a minus ib. Now let us see some examples to understand more. Find the modulus and conjugate of the complex number 3 plus I. So our complex number z is given by 3 plus I. First we need to find the modulus. So modulus of z can be found out by using the square root of a square plus b square. That is mod z equal to square root of 3 square plus 1 square, which is equal to root 10. Now we need to find the conjugate of the complex number, which is given by z bar is equal to 3 minus I. Next, let us concentrate on the multiplicative inverse of a non-zero complex number z is given by the inverse of a z. That is, z is equal to a plus ib. Z inverse is equal to 1 by z, which is equal to 1 divided by a plus ib. It can also be found using the formula z inverse is equal to z bar the whole divided by modulus of z square. It can also be written as z into z bar is equal to modulus of z square. Now let us see an example. Find the multiplicative inverse of 2 minus 3i. So our result is equal to 2 minus 3i. We can find it in two ways. First, let us solve this using z inverse is equal to z bar divided by modulus of z square. So first we need to find z bar. Z bar is equal to conjugate. So it is 2 plus 3i. Now we need to find the denominator, that is modulus of z square. The modulus of z square is equal to square root of 2 square plus minus 3 square the whole square. And on solving, we get it as modulus of square is equal to 4 plus 9, which is equal to 13. Alright. So z inverse, substituting the value, we get it as 2 plus 3i the whole divided by 13, which is equal to, separating the term, we get it as 2 by 13 plus 3 by 13i. Now the second way is, we have a z is equal to 2 minus 3i. First find 1 by z. 1 by z is equal to 1 by 2 minus 3i. Now multiply and divide by its inverse, that is 2 plus 3i. So 1 by z is equal to 1 by 2 minus 3i into 2 plus 3i by 2 plus 3i. Now we have to use the identity to the denominator, that is a plus b into a minus b, which is equal to a square minus b square. So our equation becomes 2 plus 3i the whole divided by 2 square minus 3i the whole square, which is equal to 2 plus 3i divided by 4 minus 9 into minus 1, which is equal to 2 plus 3i divided by 13. Separating the terms, we get z inverse is equal to 2 by 13 plus 3 by 13i. So using two complex number, we can also derive some identities. Now let us focus on that now. So the first identity is modulus of Z1 into Z2 is equal to modulus of Z1 into modulus of Z2. Second identity, modulus of Z1 by Z2 will be equal to modulus of Z1 divided by modulus of Z2, where modulus of Z2 will not be equal to 0. Third identity, Z1 into Z2 the whole bar is equal to Z1 bar into Z2 bar. Fourth identity, Z1 plus or minus Z2 the whole bar is equal to Z1 bar plus or minus Z2 bar. Do you think whether these complex numbers can be represented on an XY plane, or does it require something different? Answer to this question will be covered in our next video. Now, let us summarize the concepts which we have discussed here.
Manorama Horizon. Learning made simple.